There we go. All right. So, what we had last day is we had a situation where, if you remember, we neutralized half of the quantity of a weak acid with a strong base. And so what we ended up with is we ended up with equal moles of the conjugate base and the conjugate acid. Okay, and at that point, when we had neutralized half the moles, and if you remember, we started with 4 moles of the acid, and we neutralized 2 moles of that with 2 moles of hydroxide. So 2 of those moles got converted into the acid. So far, so good? All right. So we ended up with a mixture of the weak acid and the weak base in equal proportions. Okay? So when they are in equal proportions, then that means, and we did a bunch of math around it, okay, and we did the plus x minus x, yada, 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 assume the x's are insignificant, but the main point of it is that these two were equal. And if those two are equal, then we can cancel them out. Do you remember what the point is called? When we've neutralized half of the acid.
Before the equivalence point.
It's before the equivalence point. And what's the equivalence point? The equivalence point is when we have neutralized both of them, and we've neutralized all the acid, okay? And we don't have any excess acid or base. But when we've neutralized half of it, we call that the half equivalence point. And at the half equivalence point, Ka is equal to H plus.
Half of H plus.
It's not equal to half H plus. The reason down at the bottom that it says H1 half, that means this does not mean half of the hydrogen concentration. Okay, what it means is the concentration of H plus at the half equivalence point. That's what that half stands for. Does that make sense? Okay, so just so you know that notation, it does not mean half of the H. It means the concentration of H at the half equivalence point equals Ka of the acid. Okay, so that's where we got to yesterday. You are not going to have to do any of this stuff. Like, that's a lot of work, yes. You don't need to do any of that. You just need to know that at the half equivalence point, hydrogen is equal to Ka. All right? And we are not going to do pages 68 and 9 because these are just doing the same examples but using the weak base equilibrium, which is, it'll work out exactly the same, and I don't know that it's worth our time to do that. So we're going to skip that, 68, 69. And we are going to move on to when all of the weak acid is neutralized. So not half of it now, we're going into where all of the weak acid is neutralized. What do we call that point where all the acid is neutralized? That is called the that's our complete equivalence point, which we don't call complete equivalence point, we just call it the equivalence point. Okay? There's no excess acid. There is no excess base. So what we're going to do is we are going to calculate the concentration of the mixture when 5 milliliters of 1 molar NaOH. And I'm going to play really fast and loose again with our significant figures. And I'm going to say, okay, we've got 5 milliliters of 1 mole per liter. And that's going to give us 5 millimoles of NaOH, which is the same as 5 millimoles of OH minus, because we only have 1 OH in NaOH. So far, so good? Okay. So we got that number there. And we have added it to 5 milliliters of, remember of means times, 1 molar CH3COOH, and that gives us 5 millimoles of CH3COOH. Remember, this is step 1. What is step 1? Step 1 is the, yes, find the moles of the acid, find the moles of the base. But step 1 in this entire process, working our way to the pH before we calculate what it is once it is neutralized. First, we have to figure out neutralized. Okay, neutralization, I should say. Step 1 is neutralization. Do we really need to show a RICFA table here? Probably not, because the millimoles are the same and everything is 1 to 1. Yes? So we start with 5 millimoles, we start with 5 millimoles. They both get used up completely, and we're left with 0 and 0. How much of the weak base did we make? 5 millimoles, okay? Because it's all 1 to 1 to 1, because we added 5 millimoles there. Did we need to show all that, or could we have just, almost assumed that? Yes, we could, okay? But that shows it if we need it, and remember, you either need to write millimoles here, or here, or both, if you want to, okay? But it needs to be somewhere. Or if you're working in moles, that's also fine, but remember, it just makes it a little easier in millimoles because the numbers are nice. So now we have the only thing left after neutralization okay, there is sodium, but we don't care about sodium because it is a right? We just left it out up here because it is a spectator. Okay, so we don't care about that. So the only thing that matters in terms of pH after neutralization is this base. Okay, and remember that is a base. And if we have some base, what would you expect the pH to be? If we've got a solution that contains some base?
Above 7.
Above 7, okay? So therefore, the pH will be greater than 7. That sometimes surprises people because we've reached the equivalence point. Yeah, normally people are like, the equivalence point, we're pH 7. Yeah? But that's only when the base you produce doesn't hydrolyze. Whereas this base, and that would be something like Cl minus. Cl minus will not hydrolyze. It is unable to act as a base. But here we have a base that will hydrolyze. So we can then write our weak base equilibrium. And in this case, we are going to use the weak base equilibrium. You could do the weak acid equilibrium, but it seems really weird to do that when all we've got is the base. But you could. It would just everything would shift to the left instead of the right. Anyway, we've got our weak base here. So this is step 2. Remember, we do the neutralization, and then we take a breath. We've done that part, and now we're going to say what happens to the stuff left after neutralization. In reality, is this all happening all at once? Yes, it is. But we separate it because it's easier for our little brains to comprehend. At least it is good for my little brain to comprehend. Okay? So how much of that did we have? We had 5 millimoles, and the total volume was 10 milliliters, so we have 0.5 molar. 0.5 molar. These are at 0 and 0 because we didn't make any of those in the neutralization. We have to be shifting to the right because there are zeros there. We have to be shifting away from that. And of course, we're going to then write our Kb expression. And then we have to find Kb. If we're using Kb, which is Kw over the Ka of the conjugate acid. Okay, so we got that there, and we get 5.56 times 10 to the negative 10. And shove everything in there, assume x is insignificant. Solve for x squared. Solve for x. What was x? X was concentration of hydroxide. So that's our concentration of hydroxide. Find the POH, find the pH. And because we used because these values had 2 sig figs, our answer should have 2 sig figs. Is good? Okay. So at the half equivalence point, Ka is equal to concentration of H plus. At the equivalence point, the weak base produced will hydrolyze to make the solution basic. Are you guys good with WB for weak base? And if the weak base hydrolyzes, what tools should you use to solve for pH or hydrogen? It is weak, and it is a base. Anytime you see weak, what should you be thinking? No. When you see weak, because you might have a weak acid, okay, you're right that it is going to be Kb here because it is a base. But the word weak in particular should tell you you need to use a, not RICFA, because that's when you're doing the neutralization. Okay, the neutralization, we use the RICFA table. If you were away yesterday, the F stands for final because we're going to completion up here. Okay, and so the final values are there rather than equilibrium values because it goes all the way. But if it is weak, what do we use? Rice. God bless you all. Okay, rice. Because it is a base, we're going to use Kb. There were still a few people who were given a weak base on the quiz and then found the Ka and tried to do something with it. I don't know. I don't know. I don't know how to make that stop other than to say you need more practice. Because if you do more practice, then you're less likely to make those mistakes. I can't tell you any more ways than if it's base, use K, B. Base. K, B. Base. K, B. Base. B for base. Maybe that'll make you remember it because I stood up here like I was having some sort of weird seizure. I don't know. I'm willing to do anything for your learning, almost. Okay, so here we go. So that is what we do when we have a strong base plus a weak acid. So we can find the pH at the half equivalence point. We can find the pH at the equivalence point. And those are the only two we really need to be able to do. We can also find the starting pH, but then you've just got a weak acid, right? So you're like, you know how to do weak acids. When an excess strong base has been added, that is after the equivalence point. Okay, so we've neutralized all the acid is gone. We're just adding extra strong base. Once again, we will do the neutralization. So we have 6 milliliters times 1 mole per liter is 6 millimoles of NaOH, or we can just say that's 6 millimoles of OH minus because they are 1 to 1. We also have 4 milliliters of acetic acid, so we have 4 milliliters times 1 mole per liter is 4 millimoles of CH3COOH. So we have our hydroxide, 6 millimoles. We have our acetic acid, 4 millimoles. How much gets used up of each of those? 4, because we can only use up 4. That's our limiting reactant. Okay, that's our limiting reactant. That is our excess reactant, XS for excess. So we use up 4. That means we use up 4, and that means we make 4 millimoles of the weak base. So we end up with 2 here, and we end up over here with 4. So what do we have left over? We've got OH minus 2 millimoles, and our total volume, 4 plus 6 is 10 milliliters. So we have 0.2 molar OH minus. CH3COO is a weak base, and we have 4 millimoles of that in 10 milliliters. So we end up with 0.4 moles of weak base. So you have hydroxide here, and this weak base will make hydroxide. How much hydroxide will the weak base make in comparison to this 0.2 molar? Like tiny, tiny, right? Because Kb is what kind of a number? Kb is really small, okay? So the weak base will produce OH, but the amount it produces will be insignificant next to the OH from the excess NaOH. We can prove this, okay? We can say we have 0.2 molar OH from the NaOH. Here is our Kb table, all right? Here's our rice. You know, we have some hydroxide here. This is how much we had from the NaOH. You don't have to be able to do this math, okay? And this is how much we had of our weak base. Because this is 0, which way does it have to shift?
To the right.
Has to shift to the right. Plus, plus, minus, and we end up with 0.2 plus x, and over here we end up with 0.4 minus x, and then the weak acid form, we end up with x. All the math, math. Find that there's our Kb expression. We found our Kb, taking Kw over Ka of the conjugate acid. Let's assume x is insignificant to make it not a quadratic. Solve for x. There is x. What was x? X was, oh, that's not hydroxide. I'm so sorry. No, I just need to get this thing so it's writing. There we go. That's not hydroxide. That's just x.
Oh, but X.
But x is this amount here. We already assumed it was insignificant. Is it insignificant? Yes, it is, because 10 to the negative 9 is much, much smaller than 0.200 molar. And remember, this came from the extra.
But we don't have to do this.
So you don't need to do any of this, right? I'm just proving that you don't need to do any of it. All you need to do is say, how much OH did I get from the extra NaOH? And I can just ignore the base, the weak base. Yes? So after the equivalence point, the OH, the PaOH, all of those depend only on the strong base. You can just ignore the weak base. It is insignificant. Is good? So if I were you, and if I were one of those people who like to make my own notes afterwards, you know, just to summarize things, I'd be like, ooh, actually, look, I am one of those people who likes to summarize things afterwards. Look at this, before the equivalence point. This is AP Chem only, so we're just going to cross that out. That's at like some random point before the equivalence point. At the half equivalence point, half of the weak acid remains unreacted, and basically, thank you. Half of the weak acid remains unreacted. Half of the weak acid has turned into its conjugate base. So hydrogen at the half equivalence point is equal to Ka. At the equivalence point, it is only the conjugate base that is present, and you're going to use ricin Kb to find OH. And then after the equivalence point, it is only the excess hydroxide from the strong base. And I was like, this is way too wordy. Look, we can make a summary of the summary. How far along is the reaction? If there is no base added, you have HA only, what tools are you going to use to find the pH? Ricin Ka. Before the equivalence point, remember, we're going to ignore this because we're not AP. Okay, bye-bye. At the half equivalence point, what do you have? You have both HA and A minus, and those two are equal. So at the half equivalence point, the hydrogen is equal to Ka. And remember, that's the, maybe I should just write it like that. It's the, that's hydrogen is equal to Ka. I find, yeah, that half is sometimes confusing to people because they think it's half the concentration. It's not. We said that already, but just to remind you. After the equivalence point, the only thing we have is at the equivalence point, A minus only. That's our base. And so you'll use ricin Kb. And then after the equivalence point, excess OH only. You can ignore the base that's also present, and you just take the excess moles and divide by the total volume. Is good? And this is how we're going to do a titration curve. Okay, so if you were asked to draw a titration curve, you could use each of these points to give you the start, the halfway to equivalence point, the equivalence point, and then the end. And you'll see a curve that looks like this. Okay, and we'll get into the actual curves themselves later. All right, so there is some questions there. And let's see which ones, if there are any that we need to get rid of. AP Chem only, so you're going to cross out number 4. Yep, and that's it for that. Okay.
Buffers, all of them.
Okay, so let's see, what time are we at? We've got a little bit of time. There's a whole bunch of buffer videos. I have, like, you can, if you're like struggling, you can watch me talk about buffers for a long time, 50 minutes. Or you can watch Mr. Colger, who talks about buffers for 14 minutes, and then 7 minutes, and then 5 minutes. That sounds kind of nice, right? That's a lot less. That's only 25 minutes. Okay, so half the time you can spend with Mr. Colger. All right. Would we like to watch some videos by Mr. Colger, or we? Anybody care?
Yeah. I mean, like, are we gonna go over?
We're going to go over stuff anyway. Okay, let's go over stuff anyway. Here we go. Intro to buffers. Oh, do we want to do this today? Do you know what? Because you guys showed up on senior skip day, you know what we're going to do? I'm going to give you some time to practice these things for your quiz on Friday. Does that sound like a plan?
Yeah.
Yeah, okay. So what we're going to do is, let's see, what would be good for you to do in terms of hydrolysis?
The Rigfa table will be on there, right? Yeah.
The RICFA table will be on there. So let's take a look at that. You know what I would do? I would start with 5.3D. 5.3D, that is pages 51, 52, 53. Actually, no, this is notes. Oh, no, it's not. Oh, no, it's not. It kind of is, but it kind of isn't. So, yeah, let's go to page 51 and do this together. Just for starters, because this is going to review a lot of the stuff for hydrolysis. Okay, page 51. You might be given a list like this where it's like, find the pH of all of these solutions. Anytime you're just told find the pH of a solution, you won't necessarily know if it's an acid or if it's a base or if it's a salt until you think about it. Yes? So in each of these cases, let us determine, is HCl an acid, a base, or a salt? It is an acid. And if it is an acid, so you ask what kind of compound do you have? And then if it is an acid or if it is a base, you have to ask yourself, is it strong or is it weak? HCl, is it strong or is it weak? Strong. So go through each of these and decide, is it an acid, is it a base, or is it a salt? If it's an acid or a base, is it strong or is it weak?
I have Howard coffee taste. I can call doesn't rewrite it. H3. Oh yeah, it's 3. Yeah, that's the next thing.
Let's just figure out what they all are. Actually, salt.
E is yellow. Oh yeah. So. Because we have strong salt. No. It's like on the like, is there a hydrolysis or that? Is there such thing as strong salt? Cool.
All
I would have,
because they're not.
why not? Strong salt, cool. Not strong.
Yeah.
But strong salt. Strong salt. If that's a thing.
Okay, we're gonna go eat that one.
No, like some salt, salt, we didn't.
Okay, so hopefully you guys got that this is a strong acid, this is a weak acid, and this is a Weak acid. How about SrOH2? What is that? That is a base. I'm just going to go with B for now. Is that a strong base or a weak base? That is a strong base because metal hydroxides are strong bases. Then we come over to NH3. What is NH3? It's a weak base. And then we have calcium chlorate. That is a salt. NaCN is a salt. FeNO3 is a salt. If you have a salt, what should you be doing with the ions? You should be separating them and seeing if they hydrolyze. So let's separate our two ions here. We have Ca2 plus and ClO4 minus. Here we have Na plus and Cn minus. And we have Fe3 plus and NO3 minus. Does calcium hydrolyze? No. How do we know? Not feel creepy. Or NH4. Does ClO4 hydrolyze? No. So there is no hydrolysis. So the pH will be 7. If we have Na, will Na hydrolyze? No, it is not feel creepy nor NH4. Will Cn hydrolyze?
Wait, how does chloride that one not hydrolyze? It's a strong acid, but it's part of the strong also.
Does Cn minus hydrolyze? Yes. HCN is weak. And so is Cn minus going to give us acidic hydrolysis or basic hydrolysis? Is Cn minus an acid or is Cn minus a base?
It's a base.
Cn minus is a base. It has to be a base because it doesn't have a hydrogen, right? I'm just going to write hydrol because I'm running out of room. Okay? Hydrolysis. There we go.
If the metals are
Well, let's look at our next example. Fe3 plus.
yes.
Yes. NO3 minus? No, because HNO3 is strong. HNO2 is weak, if you're looking at HNO2. So, anytime the cation hydrolyzes, is that going to be acidic or basic? It's going to be acidic. And if you have Fe3 plus, how is it possibly acidic? It ain't got no H. Cn minus didn't have an H, it was a base. How is Fe3 plus acidic? How does it have hydrogens to give away?
It produce hydrogen reaction, right?
Go look it up on your table.
with HL, H2O, H2O.
What does iron do?
Oh, it should be H2O. It should say.
There are 6 waters attached to it when it dissolves in water. It grabs onto 6 waters, and the waters provide the hydrogen for it to be an acid. Now, we're not going to do all the math associated with these, but what we're going to do is we're going to go through and you're going to tell me the tool or tools that you will use that you would use to find the pH of these solutions. What would we use to find the pH of an 0.35 molar solution of HCl? We would use stoichiometry because it's strong. Strong, use stoichiometry, right? The concentration of H plus is just equal to 0.35 molar. We don't even really have to do anything for that, right? I can show that line, that work on one little line here. Yeah? We could find the pH, but you know what? I know you know how to find pH, so I don't care. We're just like, what direction would you go to get there? Yeah? What would we use to find the pH of a 0.35 molar solution of HF?
Right.
It is weak, and every time it is weak, you should use rice. Weak, rice. And we are going to now use a K what? Ka, because it is an acid. And we're not going to worry about doing that because that sounds like a lot of work, okay? Here we have H3PO4. It's a weak acid. What will we use? Rice and? Okay. A. The only thing about this is it has 3 hydrogens. How many hydrogens come off? Only 1 hydrogen comes off. In the reaction. Strong base. What tool do we use for strong base? Stoichiometry. Strong, ST. ST for stoic. What is the concentration of hydroxide if we've got a 0.35 molar solution of SROH? 0.7. Why is it 0.7 and not 0.35? Because there is a 2 there. Weak base. It's weak. What tool should we use? Rice. It's a base. What tool should we use? KB. This salt where there is no hydrolysis, you don't have to use any tools. You just say it's pH 7. When you have Cn minus, it is a base. What should you use? Rice and KB. When you have Fe3 plus, It's acidic. What should you use? Ricin Ka. So anytime you're given a substance, is it an acid, a base, or a salt? If it is an acid or base, is it strong or is it weak? If it is a salt, do you have anionic hydrolysis, which is going to be basic, cationic hydrolysis, which is going to be acidic, or do you have no hydrolysis, which is going to be pH 7? And then there's just examples for all of these. You know, all the ones where we didn't do the math, all the math is given here. So if you're interested, you can try it. Okay? I would say to practice for this, you would like to do acids, base, and salts extra practice. Let's try 5.3e. That'll do the hydrolysis part. And then the strong acid, strong base part. Let me write that up here. 5.3e. And then we did page, you could do 64, numbers 3 and 4. Okay. And that'll give you a little extra practice with the mixtures of weak, strong acids and bases. Okie dokie. And I'll take attendance while we're doing that.